Hi again, let's continue with our talks. The next one is going to be in English, so remember that we have live translation in our Discord server. This talk is about Bluetooth hacking. If you are interested in wireless security but have no idea where to start, this talk is for you. Yiska, the presenter, is a specialist in Bluetooth security, and she will talk about the current state of Bluetooth security and how to find bugs in its specification and implementations. So let's welcome Yiska with her talk, Bluetooth Hacking 101.
Hello everyone and welcome to the talk Bluetooth Hacking 101. I've been working quite a lot in the past on Bluetooth and developing my own tools, but I've also been supervising students who build even better tools and also tried tools by other people who were trying to hack Bluetooth or even successfully hacked things there. So you might ask yourself, why do you even want to hack Bluetooth? Well, everything is better with Bluetooth, as we already know. And because everything is better with Bluetooth, Bluetooth is everywhere, and also everything can be hacked with Bluetooth because of this. And if I say Bluetooth is everywhere, I mean like really everywhere. In your smart home, in your car, in your smartphones, in your IoT, in your headsets, in your medical devices, and even a lot of other places. So if you can hack Bluetooth, you can hack almost every device. But actually there are two types of Bluetooth, and you might not have heard about this before, but there's classic Bluetooth and there's Bluetooth low energy. And classic Bluetooth is what you know as, for example, your headset or your car and so on. They typically have the classic Bluetooth, which has a high data throughput but a short battery life. And then there's Bluetooth low energy, which you would see in IoT devices. It has like a low data throughput, but a long battery life. For example, with a button cell, you could like survive a full year just beaconing some data around. So these are the two types of Bluetooth, and you need to distinguish them. They have two different physical layers, so it's not really important for us what the difference is here, but it's important to know that the Bluetooth LE physical layer has a different modulation scheme, and it's usually having a very wide distance between each event. So here it says 1.25 milliseconds multiple of them, but usually it's like every few seconds if you want to save energy. And then there's actually some changes happening to the Bluetooth specifications. So data packets in the newer specification become larger, the physical layer changes a bit and so on. And in Bluetooth 5.2, they even introduced LE audio, but this is nothing I've seen in a device so far, except from proprietary solutions that are not the official Bluetooth LE audio. And then what you also have is on top of these layers of the physical layer, there's ACL, which is for data transfer, and it's pretty much the same for the two. And also the way how they handle encryption and keys is very similar, even though it's called slightly different. It has like a few differences, but it's like almost the same on the upper layers. Now, if you want to hack Bluetooth, there are a couple of setups that you can take. And the first one is like you just have a lot of money and you buy an analyzer that can already do all of this. It depends, or even there are differences if you want one that really can do also classic Bluetooth and so on. You might end up paying a lot of money. So they start at something like $10,000, but it might be even more than this, more like 70,000, depending on what you want to do. So with money, you can, of course, solve this issue. And if you want to start Bluetooth hacking, this is exactly what you want to invest, right? No, not really. But the good news is if you just want to hack Bluetooth LE, what you can also do is you can buy some microcontrollers with some Nordic chips on them. So the microbits have these. And there is a very nice maintained project. It's called BTLE-Jack. And with BTLE-Jack, you can actually sniff Bluetooth LE traffic and also manipulate some in this. But actually, because of the hopping and so on, you actually need 3 of them, but still each of them is like $15. So 3 of them is still an investment you might want to do when you start with Bluetooth hacking. And the next variant of a setup is a bit different. So this works for classic Bluetooth and Bluetooth LE, but again has one restriction because you need to have a device under your control. So this wouldn't work between a headset and a car because you cannot manipulate the headset or the car. But as soon as one of the communication ends is under your control, you can actually use our internal Bluetooth suite, and maybe you need to jailbreak a router device on Linux and macOS. It just works without this. And then you can manipulate the traffic on one of the ends instead of over the air. And now the next part is like, if you want to hack a connection, it somehow needs to be insecure. So at least if it is encrypted. So you need to understand how the encryption works in Bluetooth. And for this, you need to distinguish between two parts. So first of all, there is some initial pairing. This is the part where you get the numeric comparison, for example. So you have two devices where you get this number, and then you need to compare it and say cancel or pair. This is something that you do once, and then you have this trust between the two devices. And then later on, you have sessions. So each time you connect, you have like kind of a session key. And this one is derived, so it's not exactly the same key, it's just a derived key that is then used for the session, and it can also be rekeyed and so on. And the only thing that prevents from a machine in the middle attack is this initial pairing. So when you do this numeric comparison or also passkey entry. If you look into this dialog, so this is what you see on iOS right now, then it even says like, do not enter this code on an accessory. So that means you have to compare the number, you don't have to enter it somewhere, because we can actually confuse these two methods. And there we also already start with the attacks. So the secure simple pairing, as you might know, is maybe not that simple. Some of you might have already tried to pair Bluetooth devices, and often you need like multiple attempts and you stop reading what is there. You just click, 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 and then like at the third attempt, finally, you paired a Bluetooth headset. And so it's not simple. And I also think it's not secure. So it actually started a while ago, like back in 2005, that someone says like in the old Bluetooth pairing that is now called legacy pairing because it's considered not to be secure, you can actually crack the pin that you have to enter on one device just within like a few seconds back then. So something that you could also do in a live connection. And so they fixed this with the secure simple pairing scheme, but they said for Bluetooth Low Energy, yeah, I mean, we just don't want to do that many computations, so we do something simpler than the secure simple pairing, and this has also been broken in 2013 and so on. So then they adapted the secure simple pairing as LE secure connection, so it's almost the same but under a different name to the LE part of the specification. And someone also has proven that secure simple pairing is secure like around 2007. So yeah, of course, then there are no attacks, right? But there came quite a lot of attacks. So the method confusion where you have this passkey entry versus the numeric comparison. But then there are also like, for example, the knob attack, which is not the initial pairing, but then in each session key, you can actually specify the amount of entropy that goes into a key. And this is a setting that like it's just an additional message, and the stacks actually implement this. So you could like downgrade the encryption within a session. And so it just goes like this, and there are probably even more like this. But so since this elliptic curve attack in 2018, it really started off like just all those specification compliant attacks. But it's not an issue because it's like it's all scientific research, and the tools are like really crappy to use. So there's not like one tool that breaks them all. Anyway, you still need to choose your weapon, so to say. So how do you start? Well, there are two parts. So first of all, here this part, the over-the-air connection might be encrypted, but the chip decrypts it. So within the operating system, you would always see plain text, except from if there is the smartphone app or like even a cloud encryption. So then you would have an encrypted connection, but usually it would be plain text on the host. And this is something that you can like already break. So if you have Bluetooth LE, there's BTLE jack. Sadly, Ubertruth is not that well maintained and does not really work for classic Bluetooth. So you would go for BTLE jack. And if you are happy and like if you're lucky, and then it might just be like that there is also an old LE legacy pairing, and you can work with crack LE to break the encryption. The next part is that you could impersonate a device. So this is something you could do with internal Blue or also like the microbits or other Nordic semiconductor devices, if you understand everything about the protocol. Or the next option is if you are on the device itself, you can hook into the Bluetooth daemon or the Bluetooth chip itself. The Bluetooth chip might be required depending on the layer you want to interact with. And the last option is that you just hook into the smartphone app. So this might be helpful if the smartphone app does additional encryption that is not handled within a cloud part of the IoT app. And this is something you can do with Frida. So there are a lot of tools depending on what you want to achieve. The two on the left-hand side are probably the most powerful, but it requires a device that's like rooted or jailbroken, at least on iOS and Android. On Linux and macOS it just works as it is. But then again, as I said, not all devices might be under your control. And the next part is the protocol analysis. So how does Bluetooth even look like and what kind of protocols are there that you could attack? So first of all, it starts very low on the link layer. So there's some link management. And the interesting part here is that the link management is not really transparent to the operating system. So the operating system, for example, it would just say like, let's connect. And then you would have the link layer, and the link layer tries to establish a connection. And if that works out, it would say, yeah, everything is okay. So it would just send an HCI event that says success, but it could also be a page timeout. So after a while, if it doesn't work, it says page timeout. And all the messages that are exchanged here to like keep a connection alive and so on, is just stuff that's not sent to the host. So there's also like null packets to keep a connection alive and all kinds of weird stuff that you probably wouldn't see on the host. And this is also the reason why I think like a lot of this research into the pairing and encryption schemes did not take place in the past, or only like during the last 2 years, because a lot of these even depend on our internal Bluetooth suite. And of course, like also like the first people who looked into this are like always kicking off a new topic, probably for research. But like all the recent attacks are like somewhere here in those parameters and stuff that you can change if you have control over the link layer, but couldn't do it just from the operating system typically. And then on top of the link layer, there is various protocols. So there's HCI, or in parallel there's ACL, and ACL is for the data transfer. So HCI would establish the connection, but then ACL would do the data transfer on top of it. And it's like a very generic data transfer, and it exists in Bluetooth LE and Bluetooth Classic, even though it's like slightly different from the features that it supports. And in classic Bluetooth, you would get very fancy stuff like music streaming, tethering, and even file transfer. Here, it's an important part to note that like AirDrop is actually doing the file transfer with Wi-Fi and only the detection in Bluetooth. So you cannot transfer files between Apple devices and Android devices, because Android is using the standard file transfer, and that's not compatible with AirDrop. And then the last thing is that you can actually see all of this. So because this is not in the link management, but actually stuff that is sent to the operating system, you can observe it on the operating system. And on Linux, you can just use Wireshark. And then there is Packet Logger on macOS and even on iOS. So since iOS 13 and also still working iOS 14 with a Bluetooth debug profile, you can see your traffic on iOS, even though you cannot inject something without a jailbreak, but you can observe it. And on Android, there is the developer option, the Bluetooth Snoop Log, and all of these can also be read with Wireshark later. So this is really a nice thing to observe. Not everything is ACL, so there are HCI events, so Bluetooth advertisements contain data, but they are in HCI events. And then there's also SCO for headsets in classic Bluetooth, but it's everything that you can observe there. And let's start with the Bluetooth LE advertisements, because even though they are like really, really tiny packets, just a few bytes, they can do a lot. So they are just broadcasted, there's no acknowledgement. And usually this would be this application like when you power a Bluetooth LE device for a year with a button cell, and it just broadcasts some information every few seconds. And it broadcasts them on 3 different frequencies. So you have 40 channels in Bluetooth LE, 2 megahertz wide each of them, but you have 3 of them just in case that you are interfering, for example, with a Wi-Fi. It tops around and changes this. So it's really just some kind of random broadcasts on random channels, and eventually you get them. So nothing for a high data throughput, but at least if you have interference, there's no like very sophisticated mechanism. You just also hop around and try to sniff these. And the next part is that the sender address can be randomized or non-connectable. And this is very useful for exposure notifications. So probably the only document that has an Apple and a Google logo on it, because this one is compatible between the two. Yay. And so the sender is randomized. There is no feedback if an advertisement arrived. So this is also important because that means it's probably not exploitable, because modern exploit always need a feedback channel. And random addresses. So that's a very nice thing to build with BLE advertisements. And while Apple does much more with BLE advertisements, so this is maybe a bit scary, there is this continuity framework, and most of this is somewhat based in BLE advertisements, not all of it. But so, for example, the airdrop is advertising, first of all, like that there is an airdrop thing over BLE, but then switching to Wi-Fi for the data transfer. And then the same is like, for example, for the auto unlock, there's also first BLE notification, also handoff, and so on. So all of this is using BLE advertisements before it goes into certain states of data transfer that then are usually handled within Wi-Fi. And now something that's also super, super weird and just based on BLE advertisements is Bluetooth Mesh. So the Bluetooth SIG just thought like, yeah, I mean, advertisements are super compatible between all kinds of devices. So let's just build a mesh on top of it. So it's definitely not a high throughput mesh, but maybe something that you could have like to mesh multiple IoT lights or something, and then switch them on and off with this mesh. So this might work. Still, you need to consider there's like packet loss and just a few bytes, and like not what other people might think of as a mesh. And it's also a separate specification, so it's not in the main specification, but it's like 400, 500 pages on top in a separate document. In Bluetooth LE, you will always see this so-called generic attribute protocol, so GATT, and BLE GATT is just some kind of data transfer mode for an active connection, and it has services, and within those services or attributes you can like read and write them. I mean, they might also be restricted, so maybe you can only read them, and maybe they require prior pairing, and you can even subscribe to notifications. So for example, you could just subscribe to a thermometer, and then each time the temperature changes, you would get a new notification instead of pulling each time. And there are a lot of them that are standardized. So for the device name, for example, this is something almost every device implements the device name and also the battery level. And there might also be custom proprietary ones, and you just see them everywhere. Now, the nice part here is that if they are in plain text, you might just spoof them, for example, or exchange the information and impress your friends, like because your fitness tracker might also be using this. This screenshot was actually using modified firmware in a Fitbit Flex, but the previous versions did not encrypt the traffic, so you could actually also do this over the air if you wanted. And talking about injecting funny or invalid values to impress your friends, you can also just go to wireless fuzzing. So fuzzing is about injecting invalid traffic and then trying to even get code execution on a chip or on a device. And now you might say, yeah, I mean, what is the difference between like wireless fuzzing and so on? So, well, if you would not do wireless fuzzing, you would just, let's say, fuzz an image parser, then you would generate image files and send them, for example, to AFL++, and then it's like parsing those images and might record crashes and so on. But for this, you need to recompile it. And this is something you typically cannot do because like wireless devices, that's like very proprietary stuff. So you don't have source code. Also, the state tends to get very complex. So it's not just like you put in one packet and then something happens, but you might need to have like a paired device with an active connection and to have like all the states that the packet actually goes through and so on. And it's also hard to emulate like a full wireless stack. So usually you would do emulation if you don't have source code, but emulating something wireless is, depending on how much you want to emulate of it, it's also very hard. So the first fuzzing setup is that you just like, let's say, take internal blue or anything else that somehow changes traffic. And then you send invalid traffic over the air. It's very slow, of course, because it's restricted to the Bluetooth connection over the air. So that's the maximum speed you can reach. But if you have invalid traffic, you would very often just get disconnects, and then you need to reconnect. And there's also no feedback. So of course, no coverage of code, but also if you crashed or if you just disconnected because of invalid traffic, might be indistinguishable. And then you can like check the log files, maybe if you have them of the destination device and so on. But it's very hard. Still, you need some over-the-air fuzzing, or at least over-the-air implementation of some bugs later. So if you have found a vulnerability, you might want to build a proof of concept that works over the air. And this is definitely where you then take internal blue and craft that type of traffic. But more or less, it's like very random, especially if you want to fuzz an IoT device, like you have no idea what is going on, and you're just like, oh yeah, I maybe found a new bug with this traffic, but it's really not what you want to do. The next type of setup is when you actually hook into the Bluetooth daemon while it's running. And even there you can do kind of two things. So the first part that's like very easy is what you can do if you find the transmit receive handler. You can just like change single bytes within the packet flow, or even just flip some bits and then see what happens. But for this, you need to have an active connection. So for example, I connect to my headset and inject this traffic into the ongoing connection. And the other option is that you create a virtual connection, but while the Bluetooth daemon is running, and forge packets like within those handlers, which is easier to control. And especially with Reader, you can then also get coverage. So you even know like where in the code you have been and which parts you fuzzed. And you would also be able to observe some system and debug crash logs in addition. So you have some possibility maybe to observe what happens. And the nice part is if you hook into the Bluetooth daemon while it's running, you don't have to care about chip initialization or other states, and also interaction with other daemons. So for example, if something happens in the Apple iCloud that is connected to that pairing and so on, then it might just talk to that daemon and get some feedback instead of crashing because this is not implemented. And the most advanced option is chip emulation. For example, for fuzzing, then you're just like emulating the chip and fuzzing the chip, not the operating system on top. But this can already be very interesting. And one approach to do is like BaseSafe is doing it for a MediaTek baseband, that you just take Unicorn and QEMU and emulate single handlers. So give that handler one packet and see what happens. This might already be sufficient to find simple parsing bugs just within one handler. And it's like very, very fast because it just gives one packet to one handler, crash, no crash, that's it. Or you can also add memory sanitizers and that's it. A very different approach is something that one of my students built. It's Frankenstein. So you would actually emulate the whole modem of the chip and input certain registers into the emulated chip, do task switches and connect this to a real Linux host. And with this, you can get like full stack bugs, like for example, the host scans for devices, the modem reports devices, and then the host says, oh, I want more information about this device, and then sends another request back. And then like in this loop, there can be a bug, and it includes a lot of messages that go through this. So you can find more complex bugs, but it's also not that fast and harder to control. So if you have further questions, there will be a Q&A session, and I'm also available on Twitter or by mail. Thanks for listening.
How interesting talk. Thank you so much, Jiska, for this. We are happy to count on you in this edition of NotPinkCon. So really, really thank you so much for this talk. We have some questions. I am seeing one in the chat. What would you recommend in order to take a progressive concept logic? What should I start to is one of the questions.
Like to start what exactly? So it's a bit abstract, right? I mean, I actually think like knowing where to start, that's probably the most complex question. So like when to start a project or what to start for research. So I don't really understand the question behind it actually. So it's yeah.
It's too generic, maybe.
Yeah.
Well, but we have a lot of people asking about how did you do the finger things in your presentation? Do you want to share that trick?
Yes, yes. For this, I need to do a screen share, and I just realized I can only either share my OBS setup or my webcam. So yeah, so I'm actually working with 2 webcams for this. So I have an iPhone to my right, so that's what you can see there. And then in OBS, I actually have 2 cameras. So I have a webcam, which is just the FaceTime macOS webcam, and I have my iPhone, which I call iPhone, but it doesn't matter. And that only works on macOS. On Linux, you need a different driver to use your Android phone, for example. And then I basically have 2 cameras at once. So that's the first important part here. And then I actually have a window capture. And in the window capture, I would have my slides, which I currently don't have here. And the important part is that I set a color key to white. So everything that's white in my slides is then overlaid to the second camera, which I just use as the background. So that's the other important thing here. This one has also some filters so that I correct the color to be a bit brighter. And then so the second camera is just in the background. So I have basically 2 cameras, and that's all of it, a few filters, and then everything works live just within one recording. Yeah.
Wow, well, it's fantastic. So besides of your talk about Bluetooth hacking, we also got a trick about OBS. So thank you so much for sharing it. It's really, really interesting. Well, I don't know if there is any question. Remember that we also have the Discord. So you can go there and ask questions in the Preguntas track 1. It's for questions.
Also,
so
my Twitter DMs are also open if you want to message me. Yeah, I mean, it was a very basic introductory talk, so I hope there are just not that many questions.
Yeah, it was fantastic. Super technical talk, and we love technical talks, so we are happy to contact you in this edition. Thank you so much for sharing your knowledge about Bluetooth and also your knowledge about OBS. Thank you so much for this, and see you then.
Thank you.
Let's go for a lunch break, and we are back in an hour.